Hello everyone, this is the video tutorial for lab 11. So in this lab there are two tasks. The first one is to create a custom AXI for Lite IP to perform the following floating point operation, and the second is to test the functionality using the test bench. So before starting, let me give you a background of what we are going to do in this lab. So in the last couple of labs, we looked into the zinc part completely. So we only use the PS part of it, but it is capable of implementing both PS and PL. So we can do both the hardware and software code design in there. So far, we have only did the software design because we have only used the general purpose processor of it, that is the ARM processor, and we have written the C code for that, right? So now let's move on a little bit. So you must have, so from even I think from the lab 2 and lab 3 itself, so we are using IPs which are in the IP catalog, and we're using them quite frequently now. Also, we have used the AXI IPs for the floating point operations. So now in this lab, we will create a custom IP of our own. So far, we used to see that in the floating point operation that we can do multiply operation, we can do divide operation, but there was no such composite operation. Like in this case, we need to perform this x by t plus the square root of alpha ln by t, right? That we need to perform. So for this thing, so we will create a custom IP which will be capable of doing this operation for us, and the values of this x, t, and n will be provided by our C code, right? So basically, what's gonna happen? We will be providing the x, t, n, and alpha values from the SDK, and this IP will calculate this Q function for us, and then we will display it in the next lab for sure. So in this lab, we are only dealing with the creation of IP, and in the next lab, we will integrate it with the SDK part of it. So in the next lab, we will see a complete picture of hardware software code design, right? So how to do this, how to make the IP, how to customize it accordingly. So in this lab, we will look into it, right? Okay, so let's get started and look into the process. Right? Okay, so let's create a new project. Okay, so we do not need to specify sources at this time because we only need to make the IP. So yeah. In the board, select the Cybos at 710. Click on finish. Okay, so first we'll go into the tools and we'll create and package a new IP. So this is the console for this whole IP creation. And the next, we will create a new AXI4 peripheral. So the IP we are creating will be using the AXI Lite, basically. You can name it accordingly. Say I'm naming it Q function IP. Okay. So as you can see, this is my default project folder, D drive, ELD labs, lab 11. Although it is represent looking, as you can see, it is showing the lab 11 that IP repo. So what happens is whenever you create a new IP, so whatever is the present working directory in which there will a folder will be created with the name IP and IP underscore repo. So this IP underscore repo will contain all your IPs which you will be uh, manufacturing in future, right? So in the next page, you can see there is only one slave port. So for our purpose, we only need this one AXI slave port. So the interface type is light. So as you can see, it support full light, full, and stream. So what we are going to do is at one particular time we will be doing one write transaction. So one address, one data kind of transaction. So for that case, we will be needing only the light. We don't need the full-fledged AXI4 memory map. So a light is sufficient for us. So from the C code, at one point of time, we will be at one address, we will be writing the data, and from there, this IP will calculate, and then uh, it will give us the answer for the queue. Okay, that's fine. Interface is slave data with a 32-bit. That again fine. Yeah, so as you can see here, number of registers, and they're customizable. We can customize it from 4 to 512. So what are these registers? So basically what happens is, so how do you interact with the IP? So there is this C code and then there is this IP, right? Which is implemented on the hardware. That is the PL part of your thing. So what actually happens, so in order to communicate with the IP, so you can communicate through these registers, these slave registers. You will write at these registers and you will read from these registers. So there is a read write transactions going on between these uh, IP and the C code. And this is an interface kind of a thing that if from these registers you can actually give the values and take the answer from the IP. Right. So for timing, we don't need many registers, so we can keep a default as 4. That's not an issue. You can click on next. Yeah. So when we get to this page, instead of add IP to repository, we click on edit IP. Click on finish. All right. So once we get into here, so we get the project summary, and we have all these things. So all these things are there. So two default Verilog files you can see whenever you create a project. One is your uh, top file, and in it there is this slave file, right? So this is a template code which is already written. So in this code, what they are doing, they are just writing and reading those registers that we just specified. We specified 4 registers. So in this code, reading and writing transactions has been happening in this complete code. So uh, I hope this must have been explained in the lecture itself. So, but still, I will give you a brief introduction of what it is. So, in the top module, we are just instantiating this as a slave part of this Verilog code. So, it is recommended that you add your user logic whenever you customize this IP. You add your user logic here because it will be easy to identify uh, because there is so much of default code. So if you can see, there is 405 lines of default code. So let me just go through this code in a very brief manner because I hope you must have read this in lecture. Yeah, so as you can see, so for a light, if I talk about AXI Lite protocol and for the complete transaction, so there are total 5 channels in an AXI transaction, 3 write channels and 2 read channels, right? So for this we need multiple signals, and multiple signals are associated with this as well. So just let me give you a brief overview of what's happening. So this is a write operation happening. So these are the 4 registers we defined. So as we defined only 4 registers, so by default in this code there are 4 registers. So slave register 0, slave register 1, slave register 2, and slave register 3. Right. So what's gonna happen is, from the C code we will be writing the value onto one of this register. So we will be writing a 32-bit value complete in on one of these registers. Let's say slave register 0, right? So all the signals associated with, so you don't need to take care of how the valid, ready, and all the handshaking signals are getting generated. So that is being taken care of in this code. What we need to what we need to look into is how what thing we need to use of this code. So these slave registers 0 to 4, we can use any one of them to write our values, right? So we will be in particular using slave register 0. We will be writing a 32-bit value from our C code. Now, once it is written here, so there will be handshaking taking place. So once the handshaking is completed, we will we will divide that 32-bit into 4 different sets: 8-bit, 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 and 8-bit. So total 32-bit will be there, and then I will use those 32-bit as X, T, and an alpha, and then I will uh, pass it to my code which I will be writing to create to do the floating point operation, right? So once the operation is complete and once I get the value from those floating point IPs, what I will do is I will write it into again one of the registers. So as you can see, so in here this implements the read logic. So you we will put this value in one of this say register 0, that will be for reading purpose, and from here what we will do is we will simply read from our C code the slave register 0 after the computation. So one thing to notice in this whole code. So in this whole code, uh, there are various handshaking signals are taken care of, when to generate, how to when will the handshaking will so there will be some ready signal, there will be some valid signal. Once the handshaking is completed, those signals will be changing. So but overall the function is there will be some reading onto the registers, there will be some writing onto the register. So we will be writing something on the registers, we will be performing some computation on those values, and then we will be reading from the register, right? So that's all it is happening in this code. So that's all. Now next the next thing that we need to do is we need to perform our uh, floating point operation, right? That is necessary because we need to do this function u equals to x by t plus square root alpha ln by t. So for this particular purpose, I need to add one more source file. Let's add one more source file in which I will be so whatever we did in lab 7 and lab 8, we will be doing same thing in this particular module. All those signals will be same, all those IP calling will be same. So nothing new in that. Right, so let's say, right. Okay, so for the file location, so what you need to do is, as you can see by default, I'm getting the file location as the in the repo IP underscore repo, and this is my, so what I generated this Q function IP, right? This is the IP I have generated. So just select on this IP. So by default, this part will be there. So whatever file I will be adding new files to it will go to this directory. So it is recommended to that you add all those files in the directory where your actual IP is. Right. So this is my IP. So this is the directory of my IP. So you can put the files in any of the folder, but it will be, but just even if you just put the files in the main folder itself, that will be fine, right? So I've just added this file into q function underscore IP folder, right? So just select here. So once I have selected, click on OK and click on finish. So I have the code already with me, so I'll be using that. I will be explaining you how it is happening. Okay, so in here, let me just paste the code. Yeah. So in this particular code, whatever we did in lab 7 and lab 8, the similar thing is happening in here, right? So as you can see, all those signals are there. Clock is there, reset and is there, alpha is there, alpha valid is there, alpha ready is there. All those things are there. So one thing you can notice here, I have not used the Q ready signal here. So why I have not used here? So we'll see in a while. So for timing, you can just omit that signal from here. So Q and Q valid is there. That's fine. And rest of the things are the same that we did in lab 7 and lab 8. So let me uh, give you a brief about all those things. So in here we are converting x to the floating point representation, and we are converting t to the floating point representation, and then we are converting n to the floating point representation, and then we are converting alpha to the floating point representation, right? Then we are performing x by t using the divide operation of the floating point IP. Then we are performing log n, that is your ln n, and then we are performing ln n by t, and then we are multiplying ln n by alpha, and we are doing the square root, and finally we are adding x by t plus the square root of ln n by t. So that's how it is happening. So as you can see here, so in the ready signal, we have provided always one tick b1. So whenever the handshake happens, so I will be getting the q and q valid that I will be monitoring somewhere. So let's just wait for a while. So far what we have done is, instead of adding a queue ready signal here. We have just added a one tick B1. That is, we are always ready to accept the answer whenever the IP is ready to give us the answer, right? Whenever the IP is done with calculation of the function, we are ready to accept it. So I think so far so good. This is nothing new was there in this uh, queue function code, because you have already done it multiple times in lab 7, in lab 8, in your midterms as well. So that is fine. That should be okay. Yeah. So yeah, one thing is that you can omit the queue ready signal here. Nothing, it's not needed, right? Now, next thing is we have generated this particular module. We have X, T, and all those things. Now, earlier what we were doing, we were passing the values from the test bench. So in the earlier lab, our test bench used to be the master and our IP used to be the slave. The floating point IP used to be the slave. So the values were passed to the test bench, right? So now what's gonna happen is the values will be coming from the C code, and then we will be somehow we will be passing it to this q function underscore calci module, right? So this module should get this value from some other module definitely, because now it's not gonna get the values from the test bench. So test bench was okay for testing, but in the real world it's not gonna happen. Test bench is not gonna supply the values in the real world. It will be coming from some code definitely. So for that, I will be writing one more module, that is q function underscore top. So let's add one more design source. So what it will do is it will pass the values of xtn and the various signal needed, the ready signals and the valid signals that are needed. Those will be passed from this top module. So let's write it the top. The file location we can put the same. That's not an issue. Yeah, the file location is fine. You can click on OK, click on finish. And I'm just clicking here OK here because I have the code. You can select the port in your case, right? Okay. Now, so let me explain you this code, what's happening in the q underscore function underscore top. So input is clock, that's fine. Input is reset n, that is also fine. So we have got these four values x, t, and an alpha, right? These x, t, and an alpha values, that these will be coming from the C code. How will they be coming? How will be sending to this module again? This module will be getting this value from somewhere else, and then it is passing these values to q and okay. Now along with the, so not only the xt and an alpha we will be passing all the valid and ready signals needed in the q underscore function underscore calci module, right? So how we will be generating this? So there is one signal, as you can see, in form underscore valid. So what is this signal is? This signal will be coming from this the default, this slave code. So this will be coming from the slave code. So what it will be doing, whenever there is a value whenever there is a 32-bit value written from the C code onto the slave register 0 that we just looked into, so this inform underscore valid will go high. So the logic for this we will write in the in the slave code obviously, but for time being, this inform underscore valid signal we go high whenever there is a write transaction done from the C code to the slave register 0. That means whenever there is a new 32-bit value came from C code to the slave register 0, this inform underscore valid will go high, and accordingly these xt and alpha will change, right? So and once this xt and alpha will change, we will set the x along with the x, we will set the x valid as high, right? So that's what we used to do in lab 7 and lab 8, right? We used to put the new data, then we used to put the valid signal, right? Same case, same thing we'll be doing. So this inform underscore valid signal is just an indication for us to see that to let the calci module know that a new set of value have arrived, and those are the valid values on which you can operate upon, right? So now let me go through this code in a very precise manner. So in this always block, what we are doing is We are simply there is so we are storing value one cycle before, like one cycle earlier value of this inform underscore valid to the inform underscore valid underscore previous, right? So let me explain it with an example. So let's say this is my inform underscore valid signal, right? And this goes high at this time, right? And these are my clock periods. At here, my positive edge of clock are occurring, right? And this is again a positive edge of the clock, right? So using that always block that I just mentioned you, so we are storing the previous value like this for this particular clocks. So what we are doing, let's say this is the value that I stored at here. The inform underscore valid was 0, and at the next clock cycle I see that my inform underscore valid goes 1. So if I see here, so in the previous cycle, so according to my code, so let's say at I am at this let me name this clock cycle as 1, this clock cycle is 2, this clock cycle is 3, and this clock cycle is 4, right? So at the third clock cycle I have stored this value 0 uh, at this inform underscore valid underscore previous, right? So when the fourth clock cycle will come, uh, I will get the inform underscore valid as 1, right? So using this previous value and using the current value, what I can determine if there is a transition from 0 to 1 or not, right? So whenever I see there is a transition from 0 to 1, that simply is an indication to me that the data has a new data set has been written onto the slave register 0, and and my inform underscore valid goes from 0 to 1. So whenever there is a transition from 0 to 1, I will be getting an indication that a new data value is written on slave register 0, and I need to perform the calculation on that. So in order to do this, in order to capture this transition from 0 to 1, I am using this always block, right? So in this always block, what you are doing, we just we only need to monitor the transition from 0 to 1. That's why we are storing this previous value. We need a previous value and we need a current value. Once we have the previous value and the current value, we can comment on whether there is a transition from 0 to 1 or not, right? Similarly, we have ready signal, X ready, N ready, alpha ready, uh, T valid, X valid, N valid, and alpha valid, right? So all these things needs to be passed to the calcium module, right? Okay, so next thing is we are using some counter variables. So these are the counter variables. So we look into it for each variable we are using this counter variables t next for t, x, and n and alpha. So let's see how does it works. So what actually is happening using this counter variable, we are just measuring the handshake, or we are just seeing whether the handshake took place or not. So this is t underscore ready equals to 1 tick b1, and t underscore valid equals to 1 tick b1. So what's gonna happen? So t underscore valid is handled by us, whether the handled by the code which you have written. So whenever you put a new value of x, we will putting a new value of x. Let's say for here, let's say we are putting the new value of t, and then we are putting a new value of t underscore valid as 1 tick b1, and we are waiting for t underscore ready to get high. So once the t underscore ready gets high, that it gets 1 tick b1. So what will happen? I'm just assign the counter 2. Otherwise, if counter is 2, I will just assign it to 3. So whenever the handshake is taking place, so once the handshake have taken place, what I will do, I will just deassert the valid signal. That means I will set the valid signal to 0, right? So far we have discussed two things. One is this, how can I measure the transition from 0 to 1. For this, we have just stored the previous value, and then we are monitoring the current value using the one cycle before value, and at the current value I can comment on whether there is a transition or not, right? And the second thing is, whenever the handshake take place between ready and valid, I'm setting the counter value to 2. Otherwise the counter value goes to 3, right? So similarly for, yeah, yeah. So now we need to set the t valid as 1. So in order to set the t valid as 1, what will happen is, so we will see the transition. So whenever there is a transition, so we are seeing if inform underscore valid underscore previous equals to 0, and an informant and the current value is 1, take b1. That means there is a transition from 0 to 1. So whenever there is a transition from 0 to 1, that means a new set of data has arrived on the slave register, right? So for that, I need to set the t underscore valid equals to 1. That's what I did, right? So t valid, this is the logic for the t valid to go high, right? Similarly, we have done the same thing for this count x reg. Whenever this valid is 1 and ready is 1, count next goes to 2. And similarly for, we have done it for n, and the same thing we have done for alpha. So far, what we have got the valid signal. Uh, we have got the new value of x and valid that we have put on that. Now just think of it as we have did in lab 7. So what we used to do, we have got the new value of x. We have put it on the bus, and then we have set the valid signal high. We waited for the handshake to take place. Once the handshake have taken place, what we have done? Once the handshake have taken place, we have deasserted the valid signal, right? That's how it is, right? So next, what we did is we have just simply connected these signals to the CalC module, all those signals. Now, one more thing, and it is very important to note, is that, so as you can see, so I am assigning this queue. So there is one output, 32-bit output queue from this queue underscore function underscore top is 0. So I'm assigning only when my data is valid, right? So this valid handshake is taken care by in this 3 lines of code. So this queue will only get the value. The final answer will only be fed into this queue whenever I get a valid, that is whenever I get a queue valid. So this has been taken care of. So using this code, you have assured that whenever the value of q will be assigned, whenever the new value of the q will be assigned to this q variable, it will be a valid value, right? So that has been taken care of. So whatever will be gone into the slave register 0, that will be read from the c code is a valid value, right? So that has been taken care of. So I hope you have understood this code. So far what we have done, we have added a q underscore function underscore calci module in which all the floating point IPs have been instantiated and all those things have taken place. So one more thing is, yeah, that I forgotten. I have only added the code. So you need to, from the IP catalog, you need to add the IPs as well. So earlier we used to generate and we need to use to synthesize the complete IP. So if you want to speed that process up, there is one more thing that I need to tell you. Yeah, so fix to float. Let's say I'm using this fix to float functionality. And in the interface option, use the minimum latency and select the A reset and click on OK. Yeah, so earlier what we used to do is we used to generate. That is also a good option, but the thing is it takes time. So if you want to save some time, so what you can do is you can select the global, you can click on apply, and you can click on skip. So in that case, your complete synthesized process will not take place, and still you can get all the things that you want, right? So as you can see the symbol, earlier it used to be an orange symbol, and now there is this black symbol. So yeah, that is another way to add the IPs to your code, and that is perfectly fine. So yeah, so far we have added this q underscore function underscore calci in which we have done the floating point operations from the IP, and then we have added a q underscore function underscore top, which is taking the xt and n from the slave code and then just passing these values along with the valid and along with the valid signal to the q underscore function underscore calci, and then from here we are getting the final output of the q function, and whenever we get the valid signal from it, we will assign it to the queue, which is the queue that is the output of this queue underscore function underscore top, that we will write to the slave register 0, which then will be read from the C code. Right. So that's all for the part one of this video. So in the next part of the video, we will see how to make changes in the slave module, and we will look into the simulation of our code, whether it is working fine or not. So this is the part one. Thank you very much.